and welcome. My name is Renaud Drouin from Montreal, Canada, and I am part of the automation deployment of Hydro Quebec. Today, I will be presenting a case study for the IEC 61850 week of the Smart Grid Forums. This case study will show you how we are creating a new generation of protection and control system based on the IEC 61850 standard. We are currently deploying this new system in many stations across our territory. With a new energy management system based on 61850 coming as well, we aim to create a smart and powerful environment that will allow us to optimize the cost and facilitate the deployment of the system in the future year. At the same time, it allows us to create a strong base for future analytics, greater possibilities for remote maintenance of the system, and other needs that might not be known today. Let's begin. Substation to control center communication. So we will start with a small introduction, then we will move on to the architecture of both the remote SCADA system and the station system. Then we will talk about the common data model for Hydro Quebec, and then we will finish with the automated validation. As of now, the previous architecture for protection and control was well matured. The processes were in place. Everything was good. However, it relied on proprietary protocols and technologies, which like most technologies, eventually come to their end of life. And as in proprietary protocol, if the manufacturer of those technologies do not wish to maintain them, we get stuck with no alternatives. So at the same time, those technologies were developed at a certain point of time, but they're not necessarily flexible for future needs. At the same time, that technology, which is currently in place in most of the installation at Hydro Quebec, those were put in place a good wave in the 70s and in the 90s as well. So those are at their end of life, if not has already been reached. So there's a lot of station that needs to be modernized, and in order to be able to do all of them, the cost needs to be reduced and the technology needs to be easily distributed. At the same time, we face a little bit the same issues with the remote SCADA system, that some of the parts are now obsolete, they're hard to find for replacement, and the technology as it is has difficulty being flexible for future needs that we are now requiring with the electrification of the transport and most of our way of life. So with the architecture comes a new system for the mostly the station, but as well in line with the remote SCADA system. So right now the remote SCADA system is is different packages that are working together, but that were developed independently across the different years. So as I previously stated, with aging technologies and installation, a new EMS system was required. With this, it's time for innovation, and it was decided to go with a new system based on new hardware and software, something that would be more easily upgradable through time, and be able to better do interoperability between the transmission management, the distribution management, and all the other systems that are cohabitating with those two main systems. So we're talking about production management, work permits, and work management, and all those systems. So the complete refurbishment planned for 2024, 2025, around there, is ongoing and is being designed with all the needs in place, as well as communication in IEC 61850 between the station and in between the systems. At the same time, we need a new architecture, a new protection and control system inside the stations that will be able to provide 61850 to the remote SCADA system. So this new architecture in mind was based with 61850 in mind to take the full potential of the 61850. Communication, standardization, and interoperability across multiple vendors for that solution. It was also planned in mind to have all the needs from all the different departments that have their say inside a station protection and control system, meaning operational technologies, information technologies, ITs, telecommunications, and cybersecurity as well. The goal is to have a more flexible, better, easier, standardized solution that can be easier to manage remotely. As some of you might know, Quebec is a pretty large province, so installations are far apart, and if some of the maintenance can be done remotely, it creates synergies and improve on the costs for maintenance. At the same time, it was very long to do the homologation of new product, and those had to be in line with the previous technologies in order not to change the interaction between those protections, or it would require additional work to add those new technologies or those new IDs. So by using 61850 and the common model, as we'll see in a few minutes, this helps to reduce the cost of homologation in those solutions. So this new station architecture, it's been optimized to have as less as IDs as possible in order to have less boxes. So the commands and the protection functions were fit inside the same IDs. This allows us to reduce the number of IDs used while the commands are still effective, as they are located inside the different bays that the protection functions are protecting. So all those IDs are 61850 relays. There are some exceptions for auxiliary relays, as they are legacy technologies, but in the future years we'll work to have them in 61850 as well. And then the communication, while we're using the full potential of the 61850, so using the Goose for exchange between the different IEDs, and MMS between the bay, station, and remote levels. The IEDs are arranged along the different standard applications, you could say, so transformers, line, bus bar, feeders. So all of those are different IEDs, standardized applications with their own functions that were already in place in Hydro Quebec. And for availability and reliability, all those IEDs are redundant. The ones that are not redundant are secondary functions, such as auxiliary functions and such. So all the information coming from the IEDs, which are connecting to the fields, all those information are concentrated into the station level communication equipment. It is called UCCT, which is short for Unit for Centralized Command and Telecontrol. It's a French translation, but it's mostly relevant. So this is a Windows-based application that is running on a virtual machine. the virtual machine was deployed. As we saw, there were pilot projects for the first stations with that new architecture. And interfacing manufacturer hardware became issues in terms of cybersecurity and integration to the company's system in order to have them talk to each other, have the correct level of security. So the virtual machine is much easier to deploy and to integrate in the company's environments. So this Windows-based software does the data concentration from all the signals coming from the IEDs. As those IEDs are redundant, that UCCT will also do the redundancy management, meaning that it will merge the information from ID A and B into one signal in order to show the operators only one set of signals when necessary. And it does the communication with the remote SCADA for operation-wise, but for maintenance as well. As we saw, there's two major projects, the remote SCADA system and the station systems that are being deployed currently. As the remote SCADA is much bigger and much more complex, it's not done right away. As I said, planned for minimum 2024. As the station is much smaller and easier to deploy, those are already underway. As this creates a intermediate steps, as you can see in the diagram below, the UCCT are the new 61850 stations, but we still have some legacy stations that are still talking with the proprietary protocol that was used before. So right now we are using gateways, protocol converters from 61850 to that proprietary protocol in order to talk to the legacy remote SCADA system. Once the new system comes, then those new stations that have been migrated to 61850 will be able to talk directly to that remote SCADA, and we will use remote protocol conversion gateways in order to do the translation between that proprietary protocol and 61850. And as we migrate the different stations, we'll migrate all to 61850 until one day we should be able to be 100% 61850 in all stations. The model based on 61850 common at Hydro Quebec. So at Hydro Quebec, we decided to install a common data model for all the information that we could retrieve from any installation, production, transmission, and hopefully distribution in the near future. So this common data model is, as I said, common for all the data, meaning that where possible, we try to designate all the information based on the standard 61850, but on common ground as well. This was pretty easy at Hydro Quebec since there were already standard applications, as much as for IEDs and those and the protection functions related to them, and for high voltage equipment such as circuit breaker and disconnectors. So this allowed us to really create common information structure for each of the applications. So we decided to structure all those information based on the 61850 standard on the typical hierarchy of station, voltage level, bay, device, and then function on a function-related naming basis. We'll see how this is important in a few moments. So this allows us to have a unique name for all the installation at Hydro Quebec for each individual point, which is one of the strong suit of the 61850 standard. As the presentation was supposed to talk about the CIM, so Common Information Modeling, we don't use the CIM standard at Hydro Quebec, but we use the same philosophy. So we have a common repository where the data model is defined for all possible equipments that we've cataloged so far. It's ongoing, so if there's any new needs, it's going to be added in there. Then from different internal tools that we developed, we're able to, for now, give a SSD, so the specification file based on the 6150 standard for each of the individual stations that were migrating to 6150. In the future, we hope to provide an SCD as all the different information are known. It's a matter of developing the tools in order to provide a valid and validated SCD for each of the stations. If we look at the data model, so as I said, we're using function-related naming, and this is, as you can see, the structure based on the location code of the station, voltage level, bay, device, and then the function. Here, for the typical circuit breaker, we have two main functions, which is the command, named CM, and the supervision SP. So as you can see, all the first part, the left part of the logical device is unique, except for the function when it comes to the same device. Then within that same function, we have typical signals, and all those signals are, as I said, with the standard applications already defined at Hydro Quebec, there's not much choice in those signals. So let's say for a command module, of course, we have the position, we have the one retrieved from the fields based on the XCBR1, and the one as read by the command module. Most of the time it's the same, but in case there are some discrepancy, and it's been planned for the sample value and merging unit when we come to that in maybe a few years. The command, of course, is on the CSWI as intended by the standard, and then we could have different local indications based on the circuit breaker model. If we have a local remote inside the circuit breaker, it's retrieved through the XCBR, and the bay level local remote or the station level local remote, those are pretty much always there. Those are defined more at the ID level or at the UCCT level. So those are also defined in the command function of that circuit breaker. So despite whatever circuit breaker we are looking, we'll pretty much always have those signals. Same for the supervision. This will change based on the type of circuit breaker, voltage level. But as I said, those are standardized. So there's 5 or 6 type of, let's say, low, medium voltage circuit breakers. So it's easy to regroup and to have different kinds defined under the same points as always. So those are defined under the supervision model. And as you can see, the logical device of it is almost identical when we're referring to the same device. Now, I talked about the function-related naming. This is what we are using at Hydro Quebec. It asks to have a bit more complicated model defined. However, we'll see the advantage in a few slides. However, we faced one issue that there are some limitation in the IDs configuration softwares, and as well as the debugging tools that we use, that they're not always 100% compatible of displaying or easily implementing the function related naming. Most of them have been designed with more product-related naming, as it was more the standard engineering process used before the coming of the 6150. So we faced some issues in some of the IDs technologies, and it was greatly increasing the configuration time in the IDs if we wanted to go ahead with the function-related naming. All of this is if we keep in mind that we're trying to have a efficient way of deploying those stations, so an increase in configuration time is not ideal. So the station level software, the UCCT that I talked about, so this software allows us to define the function related naming going outside the station. And this is where we'll want it, because this is where we can do the corroboration between the different signal names when we merge them all. We'll see in a moment as well. So this software allows us to implement the function-related naming despite what is configured on the IED side, meaning that we can have IED product-related naming inside the IEDs and functional-related naming inside, going outside between the station and remote level. So this translation at UCCT, unfortunately, would increase the configuration time at UCCT level, meaning that you would reduce it at the IED level if we harmonize and go with what the tools allow us, but increase it at the station level. However, this is how we went because with our common data model, it allows us to generate as much the function-related naming, but as well as the product-related naming. Problem with the product-related naming, as you can see in the example here, we have the IED device, the IED name going inside the logical device, as it is the common part at the leftmost part of the logical device, while at the complete 61850 address. Meaning that we cannot respect the hierarchy in which we define all the information, which would allow us to have a unique name and complete with the hierarchy. This will be important on the next in the next slide that I'll talk about the common data model. So yes, this creates an increase in the UCCT configuration. However, because of those tools, it's easy to implement it, and because of the station level software that we are using, we can easily, with simple tools, generate the configuration and the translation. So the increase that we had in the IEDs that was transposed in the station level got reduced to almost nil with those simple tools that were developed. So we still have an efficient way of deploying those technologies. I was talking about the importance of having that hierarchy and all that merging of information. So as you can see here, this is how it will be in a few years, but much more complex because there's much more points. But for a simple example, we see that for the same circuit breaker or the same type of circuit breakers, we can have multiple ones within the same stations, within the same voltage level, and across different stations. All of those information are all grouped within the same, what we call data pool. It's a French translation. But all this pool of data has all the information of all the stations. And this is where it gets interesting, because all those stations, all those points, they're all within the same point, in the same location, and they're all named in a constructed, structured way, meaning that if we want to see, well, how much heating alarm did we get across all the different circuit breakers across all installations, then it's a simple query in order to go fetch the different information. So this is where the power comes from the data model, because everything is concentrated. As I talked about as well, we had redundant IEDs pretty much everywhere, and for operation-wise, most of the time the operators do not want to have redundant information displayed on screen if they are unique information. Well, let's example a circuit breaker alarm. Well, this alarm, there's only one alarm. It's just acquired by redundant IEDs. So within the station level, we have custom best of functions. I say functions because depending on the type of data, we're gonna merge both information into one. Now this merging is gonna be different based on the type of signal. So for a position, for example, we're gonna take either A or B, because there's no, it's gonna be a real best of. But if we're looking at an alarm, well, an alarm, we want it to come up to the operators, whether it comes from A or B. So then it's really a logical OR. And for the measurements, it's going to be an average of the of both values. Now, these best of functions always take the quality and the test flags of those data, both A and B. This allows us to take the most valid, the most recent information, and that's the one that's displayed to the operators. locally in the station, but remotely as well when we'll have that new generation of remote SCADA. So of course, what happens if both are not the same? So if both are not the same with the same quality and test flag, then we raise an alarm to make sure that that discrepancy, which shouldn't happen normally, is flagged for the operators and the maintenance crews. So if we look at the different examples, that best of, if we take the example for an SPS, if it's both the same valid and not in test, we're going to take the A or B. If both value are valid but in test, then we'll take an OR of the A and B, but the result will also have the test flag activated because both input are in test. However, if only one of these two are in test or not valid and the other one is valid not in test, then we're going to prioritize this value. So this allows us to have the best value, and in case of commissioning, it allows us to prioritize which one are still the valid for the operation of the station. For example, if IDA is in test, we're only going to take the value in B. That is when that's the normal way of working. Now, however, for different commissioning phases, we would want to validate one of the IDs that the information goes all the way to the top, meaning that we needed a test mode in order to prioritize the value in test. So if we look at the normal example that if IDA is in test and we want to make sure that all its information goes to the higher level, we wouldn't be able to prioritize that one because the other ID is still in operation. Same with IDB. With that test mode that we call the MER mode, MER being a translation for commissioning in French, when that MER mode is on, the value that are in test are prioritized over the ones invalid. Now this is just a temporary mode that we activate during the commissioning to make sure that, for the example that we have, that IDA values would go up to all the way to the top, with the IDs B still in operation and protecting that section still operation, but the information are not coming up. Same for IDB. And those custom functions in terms where there are commands, well, those as well send the commands based on the most available IDs, availability based on the health mode and communication. Automated validation. So with all the configuration and the new architecture that we defined with the model, we're having a greater system with more points in them. That means that we have much more points going all the way upstream, and that does increase the size of the validation. So how did we fix that? We reduced the time by having automated validation. Now, with the advantage of the 6150 model that we have at Hydro Quebec, it is much more convenient to validate that the signal that we have at ID level will be the same at the station level and remote level. Of course, there's the problem of the device-related naming and function-related naming. However, the same way we reduced it in the configuration can be done with this validation. So we are using a software that allows us to replace the IDs as MMS servers and an MMS client that allows us to replace the remote SCADA in order to validate that the UCCT is well configured with a third-party tool independent from the software itself. Now, those servers and clients are not enough. We need to implement as well custom script, and that's where this simulation software becomes very powerful, that with those scripts, it allows us to tailor that validation to our specific needs. So as I said, we are replacing the IDs with that validation tool as well as the remote SCADA. Now, in order to do the complete loop, we validate as well the IEDs with that validated tool in terms of MMS, but as well Goose. But this validation, as we're talking about the validation of the station, then we're using different script in order to produce transitions of signals inside the IEDs and validating as we listen on the remote SCADA side that every transition that we produce at the IED level, we also receive it. Now, this is the first validation that all the signal possible, we simulate all of them and then we retrieve all of them. If we look at a small station, it takes us only 10 minutes to validate 1,000 signals. So it's very powerful and we have all the results crunched up. The second validation that we currently have is that best of function. So now for each individual best of function that is defined, we validate that signal A and B are well defined within that same best of function, and that if there's some discrepancy signals, well, we validate all the conditions with all the results already crunched up. The third one is to validate if there are any grouped alarms that are for the operators. Then we can validate each individual inputs that they always produce the correct output. We also have future validations that are coming soon, which is a subset of different signals in order to test an alarm list or input conditions to, let's say, these best of functions, in order to validate that there's no degradation of functions when there's a new software version or an update on these functions as well. We're also aiming to validate all the commands as much coming from the remote than from the local HMI by testing all the blocking functions every time and making sure that the system responds well in all functions. What is very important here and very practical is that the model is predictable. So based on the SCD file that we have for the station, it's possible to extract all those signals automatically. So we don't need to define what we will test. We base it on the SCD that's been generated from the common data model. And that is really the power of all this model that we have. As a conclusion, we saw that with this new architecture of the protection control system being currently deployed in the stations, as well as the new remote SCADA system that's going to be deployed in the next few years, this allows us to have the basis of an efficient system to be deployed everywhere across our installations. Now, those two projects rely on this common data model that we have that allows us to generate a good part of the configuration at the beginning of the engineering process, which reduces the time and cost of deploying those solutions, as well as providing a common information model that will allow us to push further the analytics that we can have of all the information coming from those individual stations. Now, all of those are important part of this new program that's been in part at Hydro Quebec. Thank you.
Thank you so much for watching. I hope you found this video insightful and enjoyable. We post new smart grid related videos every Friday at 12 CET, so please go ahead and subscribe and let colleagues in other departments and peers in other organisations know so that they can benefit too. We welcome your feedback, so if you have any comments or questions, please feel free to post them below. Thanks again and have a great day.